All right, future chemists, scientists, doctors, and what have you. We are going to be taking a look at chapter 4. Okay, starting off with a little bit of atomic structure. I want to go in, talk about what atoms are made up of, and then talk a little bit about the average atomic mass. Okay, so you can follow along in the book. We've got the page numbers there. Okay, let's go ahead and jump on into things. Okay, so all matter, we said, can be broken up into two things, right? Mixtures or pure substances. And those pure substances get further broken down into compounds and elements. Okay, so when I look at a compound, right, so say I've got like something that looks like this, all right, or an element that's just a bunch of the same type of atom, right? We've been throwing this word atom around, right? An atom is just the building block of matter. Everything that we are made up of or interact with are made up of different atoms, and they're just combined in different ways to make different molecules, right? It's kind of like a Lego set, right? If you break apart the Legos, you can rearrange them and put them together in different ways to make different things, right? Same thing with atoms. We rearrange them in different ways and we make different molecules. Okay, so way back in the day, scientists have done lots of different kinds of experiments that have shown us that atoms are actually not the smallest kind of matter, right? They actually can be broken down into 3 subatomic particles: protons, neutrons, and electrons. Right? And I'm not really going to get into it, but you can even break those up further down, right, into quarks, bosons, gluons, neutrinos, all this kind of fun stuff. Okay, so if you're really interested in that, I highly suggest you guys check it out. It gets some really weird, goofy stuff, but it can be really kind of cool. Okay, but let's focus on the atom. Right? And like I said, there's 3 subatomic particles. Right? We have protons, neutrons, and electrons. Okay, protons, right, symbolized by P+, right? Their location is in what we call the nucleus. Okay, the nucleus is the center part of the atom, right? So if here's my atom, the nucleus is a very small, very dense piece of matter in the center of my atom, and there's going to be electrons going around it, kind of spinning around in orbit. I'm sure you've probably seen, like Simpsons cartoons and stuff like that. Picture of an atom looks kind of like that. That dot in the middle, that is the nucleus. That's where the protons are. Protons, they have a positive charge, okay, and their relative mass is 1. Okay, I'll get to what I mean by that here in just a moment. The actual mass, 1.67 times 10 to the negative 27 kilograms, right? Very, very tiny. These are super small particles. Okay, neutrons, right, kind of like the name implies, they are neutral. Right? So I'm just going to put none there. Okay, their symbol is N with a 0 because it's no charge. And they are also in the nucleus, right, in that central part. Their relative mass is the same as a proton. They're a 1-to-1 mass. Okay, the actual mass, therefore, is 1.67 times 10 to the negative 27 kilograms as well. Electrons are the odd man out. Okay, electrons, E minus, their location is in the electron cloud, right? That's orbiting around the nucleus. Okay, they have a negative charge, and they are very, very tiny even by atom standards. They're approximately 1/2000th the size of a proton or a neutron. Okay, 9.11 times 10 to the negative 31 kilograms. Extremely tiny. Okay? So, modern atoms, the way we typically think of them, is the most of the volume, the size of the atom, is made up of that electron cloud. Okay? Which is actually just empty space. right? There's a lot of space between those electrons because they're so tiny. Okay? And most of the mass of the atom is made up of those protons and neutrons. Right? I need 2,000 electrons to match the mass of one proton. So protons and neutrons make up the majority of the mass. Okay? So let's talk a little bit about how atoms can be different from one another. Okay? First off, we have different kinds of elements. Right? If we look at the periodic table of elements, there's one up on the wall in our classroom. Okay? There are 118 different elements. Okay? But what makes an atom of hydrogen different from an atom of helium, or gallium, or ruthenium, or rhenium, or tungsten? Okay? And the big thing is the protons. Right? The protons define what element we have. Hydrogen is always going to be one proton. You'll never find a hydrogen atom with 2 protons or 3 protons. You'll never find a helium atom with just 1 proton, right? Because 1 proton is hydrogen. Okay, and only hydrogen. The number of protons in the nucleus of an atom identifies that particular element, right? Just like it says right here. Okay? The number of protons, we can also use that to identify its atomic number, right? So protons and atomic number are always the same. How can I figure out my atomic number? Well, if I look at the periodic table, I might find something like, say, carbon, right? This big C in the middle. Okay, and depending on the periodic table, they might be in slightly different places. A lot of the ones we use have the atomic number either directly above carbon, like that, or off to the side slightly. Right, so my atomic number is this number here. Right, and down below, you'll usually have something like 12.01. Right, this is what we call the atomic mass. Right, we'll get to that here shortly. Okay, so we got that. Our atomic number, I'll also say sometimes this is abbreviated as a capital Z. Okay, so let's go on. Okay, on the periodic table, you'll note that if you find those atomic numbers, that as you read it like a book, right, starting at the top left, going left to right, top to bottom, those atomic numbers are always increasing. Okay? So, atomic number always equals the number of protons. Okay, so if I'm looking at an atom, okay, atoms are always neutral. Okay, the reason for that is because my protons and my electrons are always going to balance each other out if it's a neutral atom. Okay, if it's a different number of protons and electrons, then it's called something else we'll get to later on. Okay, but if I look at this and I look at a periodic table, you should have one in your binder right in the very front if you don't have one with you. Okay, starting off, if I look up molybdenum, okay, molybdenum is kind of right in the middle of the periodic table, a little bit down from the top of the center. Okay, it has the atomic number 42. Okay, so that means it's got 42 protons, and because it's neutral, it's also going to have 42 electrons. Okay, if I go on, right, if I have an atom that has 17 protons, okay, well, that means my number of protons is also my atomic number, so that's 17. Okay, it's neutral, so it's also got to have 17 electrons. And if I look that up on the periodic table, that's going to be chlorine, Cl. Okay, and then again, if I do this one more time, I got 22 electrons. Because it's neutral, I'm going to have 22 protons, which means I have an atomic number of 22. And if I look that one up, I have titanium. Okay, so we can find different numbers of our subatomic particles if I know one of them already. Okay, but what about my mass number? Okay, my mass number, okay, what this is it tells us the mass of an atom. Okay, but you got to remember that mass, it's going to be determined by both the protons and the neutrons, okay? Because both of them are quite large compared to the electrons, right? They're pretty much even with each other, okay? So my mass number, abbreviated as A, okay, is going to be my number of protons plus my number of neutrons, okay? But we don't always have the same number of neutrons in all the atoms, okay? That brings us to isotopes, okay? Isotopes are atoms that have the same number of protons, right? So that means they're the same element, okay? But they have different numbers of neutrons, okay? For example, okay, I've got neon 20, neon 21, neon 22. This number at the end here, that is my mass number. That's my A. Okay? So if I look at the periodic table, if I find neon, neon's all the way on the right-hand side. Neon has an atomic number of 10, so that means I have 10 protons. Okay? Because all three of these are neon, all three of them are going to have 10 protons. Right? I also know that they are atoms, so they are neutral. So then my number of electrons are also going to be 10. Okay? So then how do I determine my number of neutrons? Well, neon 20, right? I've got my mass of 20. I know my mass number is protons plus neutrons. So I can subtract my number of protons from there, okay? And I get 10 neutrons. Right? Likewise, 21 minus 10 means I have 11 neutrons, and neon 22 would have 12. Okay? So everything else is the same. The only thing that's changing is my number of neutrons here. Okay? That's a key thing, right? Because again, I can't change the protons, because if I change the protons, then I'm going to change the identity of the element. Okay? So there are some ways that we can write out our atoms so we can see what different kinds of isotopes we have. We call them isotopic notation. Okay? And so, we can do like what we see up above here. We could do the symbol with a dash and then the atomic mass. Right? Or we'll do the symbol, and you can put in the upper left-hand corner the atomic mass, and a lot of times you'll also see the atomic number, right? Or you'll see the symbol with just the mass number, right? And the reason for that is because, well, if I know it's neon, I can pretty easily look it up and find out what the atomic number is. So some people are just lazy and don't want to put the 10 there. Okay, but any of those would be fine. We get the same information from all three. Okay? Now, if you look at the periodic table, you'll note that those masses that are at the bottom of each element's square, right, they all have decimal places. Okay, so do we have only parts of protons and parts of neutrons? No. Right? That doesn't happen. Okay? What those are average atomic masses. Okay? So what happens is we use the abundance of our different isotopes. Right? So let's say, for example, that we have some different percentages of these isotopes. Okay? So neon 20, neon 21, and neon 22. Okay, so neon 20 makes up 90.48% of all neon atoms. Neon 21, only a measly 0.27%. And neon 22, 9.25%. Okay, so the majority of neon is neon 20. There'll be a few, teeny tiny amount neon 21, and about 10% neon 22. Okay, so when we find the average of all those masses, of all those atoms of neon, we have to take those percentages into account, right? And we're going to find what we call the average atomic mass. This is a weighted average. Okay, so like it says down here, okay, my average atomic mass, I'm just going to rewrite it here. Average atomic mass is the abundance of the isotope. Okay, so that's my percentage for isotope number 1 times the mass of that isotope, right? So 20 for neon 20, 21 for neon 21, right? Right? And then I'm going to do the same thing for my second isotope. Its percentage times its mass. Right? And I'm going to keep on doing that for all the different isotopes that I have. Okay? So, you got to make sure that when you do this, right, all your percentages, number 1, they should add up to 100%. Right? If they don't, something's wrong. Right? The other thing is when we plug them in, you got to remember to take your percentages and convert them to decimals. Right? So if I have 97.23%, right, converting that to decimal form, I've got to move that decimal 2 spots to the left. That's going to become 0.9723. Then I can use this in my equation. Okay, so let's take a look here. Right? Gallium says has 2 naturally occurring isotopes, gallium-69, right, with its mass here in AMU, that's atomic mass units, right, and has a natural abundance of 60.11%. And there's gallium-71, that is 39.89%. Calculate the average atomic mass of the 2 isotopes. Okay, so before I do anything, I'm going to look at this and I'm going to say, okay, gallium-69 is 60.11%. That's the more abundant isotope. So what that means is that when I calculate this out, because it's a weighted average, it should be leaning more towards gallium-69. Okay, so let's punch it in and let's see if that holds true. Okay, so I'm going to do this one down here. My average atomic mass equals the percentage. I'm going to convert that into decimal form, so 0.6011 times, I'm going to use that big long mass, so I'm going to use the 68.9256. Right, so there's isotope number 1. I'm going to add to that the second isotope. Right, and that's 39.89%, so 0.3989 times, where's my thing? There it is, 70.9247. Okay, so I would multiply these together, and then I'm going to take my answer and I'm going to add them up, right? So when I do, my final answer is going to be 69.72, right? And with my sig figs, because I'm looking at my percentages, they've got 4, so I'm going to leave this at 4 sig figs, and I'm just going to add in here AMU. Now, before I go off here, I'm going to double check. Okay, we predicted it should be closer to gallium-69 rather than gallium-71. Okay, and sure enough, okay, we're at 69.72. That's quite a bit closer to 69 than to 71. All right, why don't you guys pause for a moment, try out the problems here with the boron and the chlorine, and then I'll wrap up by going through those real quick. Okay, so we got boron with 2 naturally occurring isotopes, boron 10 and boron 11. Okay, I want to calculate the atomic mass of boron. Right, straight away, I'm going to look at this. I see boron 11 is 80%. Okay, so it should be leaning more towards boron 11. Okay, but I'm going to set this up the exact same way like we did before. Okay, I'm going to start with boron 10, so that was 0.198 for its percentage to decimal form, times, now we don't have the long form of the mass, so I'm just going to use 10. All right, and I'm going to add to that boron 11, right? So 0.802 times 11. Okay, and I'm going to multiply those out and add them up together. Okay, and I'm going to have 10.8 AMU. Okay, not too shabby. Okay. Lastly here, let's take a look at chlorine. Okay, chlorine has two naturally occurring isotopes, 35 and 37. It's asking which isotope is more abundant. Okay, well, we don't have any other information here. Or do we? Okay, if I look at the periodic table, I'm going to find chlorine. That's number 17, Cl on the right-hand side. Okay, and I'm looking at the average atomic mass underneath. Okay, the average atomic mass, 35.45 AMU. Okay, so if we remember what we were talking about before, we said that the one that's most abundant, excuse me, it's going to be closest to. Okay, so 35.45, that's closer to 35 than the 37. Okay, so that means chlorine 35 is the more abundant one, right? Again, the average atomic mass is closer to that one. But we can go one step further. We can also figure out what the abundances are for either one of those two isotopes. Okay, and it's not that hard once you think about it. Right? We know that there's a certain percentage for each one of those. All right, so if I call this one's percentage X, this one's percentage Y, I know that X plus Y has to equal 100, right? Because they're in percentages. Okay, or remember when we plug them into our formula that we don't use them as percentages, we use them as decimals. Okay, and so X plus Y, if they're in decimal form, are going to equal 1. Okay, that's going to be important here. So if I want to calculate the abundance of each isotope, okay, what I'm going to do is I am going to set this up in my normal equation for average atomic mass. So I'm going to use 35.45, because I already know what the average atomic mass is, equals, okay, I'm going to do each isotope. Okay, so I've got the percentage for 35, right, is X. Right, I'm going to multiply that by the mass, so 35. Right, I'm going to add to that the percentage of 37, Y, times the mass. But now we got an equation with two variables, right? We can't do that, right? You can't solve one equation with two variables. So I'd actually have a second equation right here. Okay? If I solve this for Y in terms of X, right, that's just 1 minus X. Okay, now I can go back, I can plug this in. Right? 1 minus X times 37. Okay, now I've got my equation. Everything is in terms of X. So now I can solve for that X value. Okay, so I end up with 35.45 equals 35X plus, I'm going to do 37 minus 37X. And now I'm just going to combine like terms. Okay, so I've got 35.45 equals 37, all right, and then I've got 35x and plus a negative 37x. Okay, so minus 2x. Right, and so then all I've got to do is finish solving here. So 35.45 minus 37. I get negative 1.55 equals negative 2x. Okay, so 1.55 divided by 2, we get 0.775 equals x. Okay, so in percentage form, that means 77.5% is going to be chlorine 35. And then if I want the chlorine 37, I'm just going to take 100 minus that. 77.5. Whoa. That looks like a better number. 22.5. Okay, so there's my abundances. And again, I can double check. I know that chlorine 35 is the more abundant one, so it's going to have the higher percentage.